In March of 2026, months before summer even started, a heat dome formed over the southwestern United States that broke every rule scientists thought they understood about how these systems work. It wasn't just early, it wasn't just intense. The way it actually built itself defied the models, and once researchers figured out what really happened, some of them openly called the mechanism behind it counterintuitive. That single discovery is now changing how meteorologists think about heat domes altogether. Here's the setup. Heat domes are supposed to be a summer phenomenon. They typically need long days, already warm ground, and dry conditions built up over weeks to form and intensify. That's the textbook version, the one meteorologists have relied on for decades to forecast these events. But in March 2026, none of those ingredients were fully in place, and yet a ridge of high pressure built over the southwest so powerful that climate scientist Daniel Swain said there has never been, in all of recorded history, a southwestern heat event that produced temperature departures as large as what was observed during this one. Not in summer, not in any season, ever. Baseball fans in Phoenix watched a game between the Dodgers and the Giants get cut short because of the heat in March. People were wading through puddles in San Francisco while the Southwest baked under record heat, hundreds of miles away. A flash analysis from World Weather Attribution concluded that temperatures this extreme would have been virtually impossible without human-caused climate change, and estimated that warming added somewhere between 2.5 to 4 degrees Celsius to what people actually felt on the ground. NOAA scientists went on to describe the resulting weather system as what's known as an omega block, a specific shape of high-pressure ridge named because on a weather map it curves into a form resembling the Greek letter omega, with cooler troughs digging in on either side, while the ridge itself sits locked in the middle. Omega blocks are notorious among meteorologists precisely because they resist movement. Once one sets up, it can hold an entire region hostage under the same conditions for days or weeks, refusing to shift east the way weather systems normally do. Climatologists warned that this particular omega block, appearing as it did outside the normals, season and fed by a mechanism nobody expected to see in March, reflected what they called a deeply alarming shift in atmospheric patterns, one that could permanently reshape how heat behaves across the American Southwest going forward. So scientists went looking for the mechanism because a heat dome this strong, this early, needed an explanation that went beyond the usual summer setup. What they found surprised even the researchers studying it. The extra heat energy didn't come from the ground baking under a stalled ridge the way it normally would. It came from thousands of miles away, carried in the form of moisture. A powerful storm dumped record rainfall on Hawaii that same month, and as that moisture condensed high in the atmosphere, it released enormous amounts of heat energy in the process. The same basic physics behind why your bathroom mirror fogs up warm after a hot shower, just happening on a continental scale far up in the atmosphere. That released heat, then got carried downwind along an atmospheric river, a long, narrow channel of concentrated moisture and energy stretching across the Pacific, and it fed directly into the upper-level ridge building over the southwest, intensifying it to record strength. Atmospheric rivers are usually talked about in the context of flooding, since they're the same phenomenon responsible for dumping enormous amounts of rain and snow on the west coast during a typical winter. Nobody had really framed them as a heat delivery system before, a conveyor belt capable of hauling energy from a tropical rainstorm straight into the backbone of a record-breaking heat dome. That reframing alone is part of why this event forced a rethink among the scientists studying it. Daniel Swain called this a somewhat complex and counterintuitive process, and it's worth sitting with why. Most people, understandably, picture heat domes as a simple story of hot, dry air getting trapped and cooking in place. Instead, this event showed that a rainstorm on a tropical island could hand off its energy through the atmosphere and supercharge a heat dome forming an entire ocean away. Researchers gave this mechanism a name, calling it diabatic ridge building, and they found it wasn't actually new. The same process had been rigorously documented years earlier, behind the infamous 2021 Pacific Northwest heat dome, the one that sent Portland to 116 degrees and killed more than 1,000 people across the region. Multiple independent research teams used wave activity analysis, storm trajectory tracking, and other diagnostic tools to confirm that event was intensified, the same way, through moisture condensing far upstream and pumping heat into a ridge that then parked itself over land and refused to move. In the years since, that 2021 event has generated more than 70 peer-reviewed scientific papers, making it one of the most thoroughly studied extreme weather events in modern climate science, precisely because researchers wanted to understand exactly how a heat dome of that magnitude could form. What they eventually confirmed, using rigorous diagnostic methods including Lagrangian trajectory analysis and potential vorticity reconstruction, is that the moisture-to-heat handoff wasn't a coincidence or a side detail. It was the central engine driving the entire event, and seeing that same engine fire up again in March 2026 in a completely different season told researchers this mechanism is far more repeatable and far less rare than anyone had assumed just a few years earlier. What changes everything is realizing this isn't a one-time fluke. It's a mechanism, one that can apparently trigger in March just as easily as July, one that connects a rainstorm on one side of an ocean to a record heat wave on the other, and one that researchers now believe global warming is actively supercharging because a warmer atmosphere holds more moisture. And more moisture condensing means more heat energy available to feed into these ridges when the right setup lines up. There's a second layer to why this heat dome behaved the way it did, and it involves the jet stream itself. As the Arctic warms faster than the rest of the planet, a phenomenon scientists call Arctic amplification, the temperature difference between the pole and the mid-latitudes shrinks. That temperature difference is exactly what drives the jet stream, the fast moving river of air high above us that normally pushes weather systems along at a steady pace. When that difference weakens, the jet stream doesn't just slow down, it starts meandering into bigger, lazier waves that can stall out entirely for days or weeks at a time. Combine a weakened, wavier jet stream with a diabatic ridge-building event, pumping extra heat energy in from a distant storm, and you get exactly the kind of record-shattering, out-of-season heat dome that hit the Southwest in March. This matters well beyond one unusual month in the desert. If heat domes can now form this early and this powerfully outside the traditional summer window, forecasters have to rethink the entire seasonal calendar they've used for decades to warn people about dangerous heat. A system built around expecting the worst heat risk in July and August isn't built to catch a record-breaking event arriving in March, and public health warnings, cooling center openings, and emergency planning schedules are all still largely built around that older, narrower window. Emergency management agencies typically ramp up heat response staffing and public messaging campaigns in early summer, precisely because that's when the historical data said the risk climbed sharpest. An event like March 2026 exposes a genuine gap in that timeline, a period when the public isn't being told to watch for extreme heat, even though the atmosphere itself has just demonstrated it's fully capable of delivering it. There's a health angle here, too, that researchers are only beginning to fully quantify. Medical researchers studying the 2021 Pacific Northwest heat dome later found measurable increases in preterm birth rates among pregnant women who were exposed during specific stages of pregnancy, with one study tracking over 700,000 births, finding an 11 to 14% increase in preterm birth odds during certain exposure windows. Researchers built that analysis by comparing the actual birth outcomes in Oregon and Washington against a modeled counterfactual, essentially an estimate of what those same birth patterns would have looked like had the heat dome never happened, and the gap between the two was large enough to stand out clearly even years later. That kind of finding underscores that these events aren't just uncomfortable, they carry real measurable physiological consequences that can follow people for the rest of their lives. And the more often these ridges build outside their traditional season, the more populations end up exposed without the seasonal warnings they've come to expect. If you want to keep following stories like this one as new climate research comes out, go ahead and hit like and subscribe, because forecasters are going to be watching for this exact mechanism to repeat. And in the bigger picture, NOAA's own billion-dollar weather disaster data backs up just how quickly this kind of extreme is escalating. The number and average cost of these inflation-adjusted disasters over the last couple of years is now twice as high as it was just a decade ago, and nearly 4 times higher than 3 decades ago. Climate Central's chief meteorologist put it bluntly, saying it's genuinely hard to keep up with how extreme the extremes are becoming, and that this pattern is changing humanity's basic relationship with weather itself, putting more people into dangerous situations at times of year they've never had to worry about before. So what changes because of all this? Forecasters can no longer treat heat domes as a purely summer risk tied to slowly baking already dry ground. They now have to watch for a completely different trigger, a distant storm dumping rain and releasing heat that gets shipped downwind and slammed into a ridge thousands of miles away. At almost any time of year, the ingredients happen to line up. That single mechanism, first clearly identified in 2021 and then confirmed again in March 2026, is forcing an entire field of meteorology to rewrite its assumptions about when and how the most dangerous heat events on the planet are actually built. The next time you hear that a heat dome is forming somewhere in the world, in a month that doesn't fit the usual seasonal pattern, remember what happened in March 2026. Somewhere, possibly thousands of miles away, a storm may already be quietly handing off the exact energy needed to build it. That's really the core of why researchers keep describing this discovery as something that changes everything, rather than just an unusual footnote in a single season's weather record. Forecasting extreme heat used to rely heavily on local conditions, how dry the ground already was, how many consecutive sunny days had passed, how high pressure was building directly overhead. Now, meteorologists also have to watch storms forming on the opposite side of an ocean, tracking where their moisture is heading and how much heat that moisture might release hundreds or even thousands of miles downwind. It's a genuinely different way of thinking about where dangerous heat comes from, and it arrived not through a slow, gradual shift in understanding, but through one record-shattering, out-of-season heat dome that simply refused to follow the old rules.